Well, welcome back. I'm future physical chemist. We're going to continue looking at catalysis. This is something that almost any chemist can use because going into biochemistry, you're going to need to know about enzymes. Going to organic chemistry, you want to know about why this is going to happen in a certain way. How does catalysis actually work? How does it affect the mechanism? So we'll look at the kinetics here of how catalysis works. Remember, catalyst increases the rate of reaction while remaining intact after the reaction finishes. Now, that usually occurs by opening a secondary reaction pathway. So the rate of reaction becomes the sum of the catalyzed and the uncatalyzed pathways both. So we speed up. Now we're going to use slightly different terms instead of A and B. We're going to use S for substrate and C for catalyst. And we're going to use SC for a substrate catalyst intermediate. That's something we form on the way to product. So we can write a generalized reaction most time where substrate binds to catalyst reversibly, and sometimes that goes to product. Then reforms our catalyst again. So following a similar idea with this Lindemann, using a steady state approximation, we can form what is the concentration of substrate catalyst intermediate. Say that K1 substrate catalyst, K minus 1 substrate catalyst intermediate, and minus K2 substrate catalyst intermediate. We got the hiccups, equals 0. Getting our substrate catalyst to the other side, dividing by K1 plus K2, this is very simple. Substrate catalyst is K1 substrate times catalyst, K minus 1, K2. And so we're going to add all those terms together as over Km, where the capital Km is equal to K minus 1 plus K2 over K1. So such that then product over catalyst, the change in product is equal to K2 substrate times catalyst over Km. However, it's difficult to measure as it refers only to species not in the substrate catalyst complex. It's much more useful to think of this as S0, substrate 0, where the initial substrate, so all the substrate is either, and they're still a substrate, as substrate catalyst, or as a product. And C0, where the catalyst is either in catalyst form or in substrate catalyst form. So solving for substrate by itself, we get substrate 0, which we can know, which is the initial substrate we put in there, minus substrate catalyst minus P, and C equals C0 minus substrate catalyst. Once again, we know a term for a substrate catalyst, the original statement, Km equals substrate catalyst times substrate is S times C. You can plug that in and have that Km substrate catalyst equals, so I'm getting essentially SC to one side, what you can say S times C. So this term S right here and this term C, if you multiply them together, we get S naught minus SC minus P times C naught, or C0 minus SC. Now, evaluating that, turn that into quadratic, it's ugly, S0 C0 minus S0 SC minus C0 SC plus SC squared minus P C0 plus PSC. Now, quadratic function says that, let's get the Km SC to the other side and get this as a quadratic. So quadratic says, so we have put all the terms together that we can. So let's evaluate this. So take the C0s out to get S0 minus P. Take the SCs out to have S0 plus C0 minus P Km plus SC squared. So you could look at this as x squared x and now if we could quadratically solve this for SC, well, this could be, we can solve this quadratically for XC. We can make these two assumptions that will make the value easily evaluable. So one, we're going to say the initial substrate and catalyst concentrations are controlled to keep SC low. So we're going to keep the substrate catalyst concentrations low. And if we only consider the early stages of the reaction, very little product exists. So the product drops out, and we're going to say that if we're keeping SC low, let's see, that SC squared is essentially 0. Essentially, we're saying, so SC times SC is going to be 0. And so we can now solve this in terms of just SC. So getting SC to the other side, dividing by all that, we have S0 C0 equals S0 plus C0 plus Km. So we get the rate, overall rate, is equal to K2 S0 C0 plus S0 over S0 plus C0 Km. So we can imagine several different scenarios with this magical equation right here. One, we have a lot more substrate than catalyst. This is the most common case because usually we don't use a lot of catalyst. So if catalyst is very low, say that S0 plus Km is the big factor. And well, further consideration, what if S0 is smaller than Km? So then the rate increases linearly with substrate concentration, where the slope of this equals K2 C0 over Km. But a more useful approach is to take the reciprocal in order to determine both Km and K2 due to the fact that 1 over the rate is equal to Km over K2 C0 plus 1 over S0 plus 1 over K2 C0, which is known as a reciprocal plot. So if we plot 1 over the rate versus 1 over the concentration, the y-intercept is 1 over K2 C0, a constant, and Km, K2 over K2 C0. So now the other possibility is what if S0 is greater than Km, which results in a very interesting simplification. So if F0 is greater than Km, then it just says the rate is dependent only on K2 and C0. So essentially, the rate is only how fast and how much catalyst we have. So this essentially achieves our rate max. Essentially, at high enough substrate concentrations, speed tops out, and it's only dependent on the catalyst concentration. So we've essentially jam-packed the catalyst as far as it'll go, and so it's only dependent on the substrate. That's if the substrate is high enough, much higher than our Km, which is essentially a bunch of constants. Now, case 2, where we have a lot more catalyst, very little substrate. In which case, that simplifies the equation where S0 drops out. Now, if this is first order in substrate, it can be just become 0 order or first order with catalyst. So it could either catalyst drops out or first order with catalyst. However, the case is typically avoided as it doesn't provide really anything new, and most catalysts are usually pretty expensive. So usually we don't want more catalyst than substrate. So gets us into like essentially enzyme kinetics, where Michaelis-Menten enzyme. So enzymes are actually a specific type of catalyst composed of essentially proteins that facilitate many. Most enzymes are lock and key mechanism. We can analyze by the Michaelis-Menten mechanism, where substrate plus enzyme, those are reversibly forms the enzyme substrate complex, and then forms the product and reforms enzyme. So overly simplistic, it will work for our analysis. Essentially, it's essentially we're going to set it up same as case one, where the initial enzyme is much, much smaller than the substrate. So set that up where the catalyst drops out from the bottom. The rate 0 is K2, S0, E0, or S0 plus Km. Km in this case is referring to the Michaelis constant and the overall rate law, the Michaelis-Menten rate law. Just like in our basic catalysis, we're going to say S0 is greater, much greater than Km. So it's usually dependent on K2 and E0 only. And we'll take the reciprocal plot, and this will, in biochemistry, is known as the Lineweaver-Burton plot. Saying that 1 over R0 is equal to 1 over rate max plus Km over rate max 1 over S0. So, which is essentially identical to the 1 over R0 Km K2 C0, 1 over S0, 1 over K2 C0. So it's essentially, we're just plugging rate max as those constants. Anyway, in this case, they give a special name to our K2, which is the turnover number, referring to how quickly the enzyme can be regenerated for use. So if we look at a plot of 1 over rate 0 versus 1 over S0, we can easily solve for our Km as long as we know our rate max. So we R0 becomes, remember, what's this? K2 S0 E0 over S0 plus Km. Plugging the K2 S0 as rate max, we find that if we find the point of the graph where the rate of R0 is half of the R max, then essentially something interesting happens. So rate 0 is R max over 2. If I divide both sides by R max times by 2, and then get S0 Km to the other side. So you have S0 plus Km equals 2, S0. We subtract S0, and then so 2S0 becomes 1S0. So essentially, if we find the point where we know our R max, and we look at the rate, so the half R max is essentially the half equivalence point of this graph. If R max half the rate, we can find the concentration at that point is equal to Km. So if we look at the half of the maximum rate, the concentration is Michaelis-Menten product. So look, reminder, what are we plotting? 1 over the rate. So we're essentially looking at, we're plotting the initial rate of a catalysis versus 1 over the concentration at the initial rate. So we're measuring the rate, we're letting a reaction run with so much substrate. And you're in 1 over the concentration, and you look at that rate and say 1 over the rate. Then you do it again with a different concentration. What's the rate? You do it again at a different concentration. And you say, what's the rate? And you keep doing this, and you have enough plots on there. And if you find enough, remember the 1 over R max is our y-intercept. So we find our y-intercept. So half of that, so 1 over the y-intercept, 1 over r max. So if say it's the y-intercept is 5. So 1 over 5. 1 over 5 is that. It's 0.2. Half of that, 0.1. So when you essentially get to a data point that is twice the y-intercept there, you're looking at where the point where S0 concentration equals Km concentration. So we can find something relatively useful for here. Now, enzymes aren't always so nice as they're straightforward. So we have things like competitive inhibition. We will just, there's a lot of things we can discuss that we won't, but this chapter does look at competitive inhibition. So we could have one reaction where they're basic, and the other one we have inhibitor, which is going to reversibly bind. Now you could also have an irreversible binding, which will screw things up in different ways. But essentially, we're binding to the spot and making it not work. So enzyme plus inhibitor, we're going to work with reversible binding of K3 to form EI, K minus 3. So we can't ever really remove the enzymes, but we can deactivate them. So now our E naught is now E plus ES and EI to include the effect of inhibition. Now if we assume K1, K minus 1, K3, K minus 3 is all greater than K2, all these guys are, so we have a pre-equilibrium approximation. Say that inhibitor, or where we said intermediate is Kc A times B. We can have K the substrate is our Km, which is essentially equal to K substrate E times S over ES. And also for the inhibitor, we have Ki E times I over EI. So since we said that ES, E times S over ES equals Km, K minus 1 is much, much greater than K2. Say that E0 is equal to, so Km ES over S. So ES over S times Km, plugging that in for that top equation. Same thing with I. ES is equal to what? Then EI is equal to E times I over Ki. And plus ES. Then, of course, let's see, to deal with getting everything in the same terms, we're going to multiply, we're going to turn E into, we just did that, E from there into ES, Km ES over S, so we can get those two terms together, add them together, and then take out ES from all parts, and say that E0 equals ES Km over S plus Kmi over S Ki plus 1. Now solving for ES in terms of E0, we divide everything to the other side. And so now we have a way to abbreviate ES, the substrate intermediate. Which can now be found, we can now find the rate of product formation because we needed ES in the product formation. So plugging that in, it's a hot mess, but say that Km, okay. Oh, so what they're doing here is in order to get S out of the fraction, they're going to say, well, you're going to multiply S over S to both sides to get K2 E naught S equals S plus Km 1 plus I over Ki. So here's where we're making some final assumptions. If we say that the E substrate plus product is much less than substrate, say the rate 0 is equal to, so essentially looking way, way back when we found S0, saying that S0, oh God, where we said S0 was, what S0 was S plus the substrate enzyme plus product. If we say those two things are much, much smaller, they drop out, and we can just say that S is equal to S0. Now, this will simplify things so that Km1 over I, Ki, we can turn that into K prime M, such that R0 is now R max S0 over S0 plus K prime M. This causes a variety of changes due to K prime M is bigger than Km. So it can be greater than or equal to K prime M. So it's always going to be, if the Ki was incredibly large, there's no I, period, that would give you 1. So it's going to at least equal Km, but it could be larger. So in this case, the slope of the Burke-Weaver plot would be greater, and that more substrate would be required to achieve the same Rmax state, which is now S0 would equal K prime M. But we can figure that out. I know that was a hot mess. So we'll stop there. Essentially, there is some graphs we can now take a look at that we're going to essentially use. You could use the rate change for substrate to find out how intermediate will affect